All right, it is about time to get rolling. So let me go ahead and get started. I'm going to start by sharing my screen with you. I will actually tell you we are in chapter 11 now. I gave you sort of an intro to the equations that we're going to be using, a description of what conservation of angular momentum is, a description of what angular momentum is, and your book talks about a lot more details than that. My main job here is to try to show you how to solve the physics problems, and then hopefully in your reading you'll make better sense of why the equations are the ones that they are and under what circumstances they can be used, that sort of thing. So make sure you pay attention to that in the reading. For instance, one of the big things is we have an equation, the summation of the torques equals dl dt, and the summation of the torques equals I times alpha. Specifically speaking, the I times alpha is not quite as general as the dl dt, just like the F equals ma is not as general as the F equals dp dt. So that's a case. But not only that, it turns out that you can apply these equations, the summation of the torques uh, equals L or dl dt, or the summation of the torques equals I times alpha, even in non-inertial reference frames, as long as the axis is fixed and you calculate the moments of inertia about the center of mass. Other than that, it talks about some rigid bodies and how you don't necessarily have to have rigid bodies for the equations to apply. They can actually be, just an assortment of literally birds flying or something like that. So, anyways, check that out. I'm going to go ahead and share my screen with you real quick, hopefully, and then we'll get started. Hmm, there we are. As always, it's definitely more helpful for you to. Ah, crap! I realized my internet's out. I gotta switch to a different internet real quick, and that means, oops, I can't do that one. Hmm. Why is it not showing my other internets? Ah, there it is. Phew, scared me. I thought I wasn't gonna be able to get there. Okay, now my internet should be working, and now I can share my screen. Sorry about that taking so long. It should pop up in a second. So now we're finally working. We're going to start with example 11.1. And you can, again, if you have your ebook open, that'd be much more helpful. But 11.1 says, example 11.1, object rotating on a string of changing length. Hopefully you've done something like this before. I remember taking like yo-yos and stuff like that, or any kind of mass on the end of a string, and you can swing it over your head like this. But if you grab the bottom of the string and pull it in, you'll notice that as you pull it in, the mass goes faster and faster and faster in a circle. And that's a consequence of conservation of angular momentum. And that's what this problem's about. So, example 11.1. We are given that there is a mass m on the end of a string. The string is actually run through a hole in the center of a table that's nearly frictionless, or frictionless is what we're assuming it is. And then a length of that string up above the hole goes out laterally and attaches to the mass. And the length of that string initially is R1 is equal to 0.80 meters. And what we're going to do is we're actually going to, let me go ahead and finish reading it first. And then I was trying to write down at the same time, and that just wasn't going to work out. So, a small mass M attached to the end of a string revolves in a circle on a frictionless tabletop. The other end of the string passes through a hole in the table. Initially, the mass revolves with a speed of V1 equals 2.4 meters per second in a circle of radius r1 equals 0.80 meters. The string is then pulled away slowly through, or pulled slowly through the hole so that the radius is reduced to r2 equals 0.48 meters. What is the speed v2 of the mass now? So we've got r1 equals 0.80 meters. We've got v1 is equal to 2.4 meters per second. And we've got r2 is equal to 0.48 meters. And what we want to know is what is V2. And of course, our solution is going to require us to use the idea of conservation of angular momentum. So remember that means the summation of the torques is equal to uh, dl dt, where L is the angular momentum and L, as your book explains, can be thought of in many, if not most cases, as L equals I times omega. And if we have the summation of the torques is equal to zero, then dl dt is equal to zero, and that means that L is equal to a constant. And that is the very definition of conservation of angular momentum. Specifically, I1 omega 1 is equal to I2 omega 2. So, if we wish to work that, you can see the drawing in the book. Does everybody have access to the book? Are everybody able to see the book? Or more specifically, is any single person unable to see their book? Because I'll need to draw all the diagrams if any of you don't have it open. Anyone? Okay. So it looks like everyone's okay with me not drawing it. All right. So what we're going to have here is conservation of angular momentum. So L initial is equal to L final. And in this case, we're just talking about something spinning around in a two-dimensional plane. And we've defined these rotational variables such that if your right hand fingers curl in the direction of the rotation of the object, then your right thumb points in the direction of that vector. And for a surface where things are rotating in two dimensions like this, then obviously straight up and straight down are the only directions we're dealing with. So I don't really need to think about it as a vector. I just need to think about it as a positive or a negative. So I'm going to say L initial equals L final and ignore the fact that they're vectors because they're both in the right direction. And that is going to give us I1, oops, that's going to give us I1 omega 1 is equal to I2 omega 2. And omega is a little weird, as is I. Specifically, when we learned about the moment of inertia, we did actually calculate, or they did give you in a table, the moment of inertia of a single point particle orbiting around is mr squared. And you can also think about that as the parallel axis theorem, because if it was a point particle and it was just rotating like this, it would have no angular moment or no moment of inertia whatsoever because it's a point particle and it has no radius. If you then decided to shift that over by an amount r, then the parallel axis theorem would tell us that the moment of inertia about this new center of mass would be, or about this new rotation axis, would be the moment of inertia about the center of mass, which is zero, plus m times the distance away from the axis, which is r. So that's why we got mr squared. Therefore, this becomes uh, specifically m times r1 squared omega 1 is equal to mr2 squared omega 2. And we also need to remember that v is equal to r times omega. So we can actually represent omega with v over r. Now with that, we get mr1 squared v1 over r1 equals mr2 squared v2 over R2, like that. And with that, you see the R2 cancels out with the squared, the R1 cancels out with the squared there, the M's cancel out, and ultimately we're just left with V2 is equal to R1 over R2 times V1, which will be equal to 0.80 meters over 0.48 meters times V1, which is 2.4 meters per second. And that gives us V2 is equal to zero point 0.8, zero point 0.8 divided by 0.48. Multiply that by 2.4, and that gives me 4.00 meters per second. And that is the final velocity when you actually shorten the string from 0.80 meters to 0.48 meters. Anybody have any questions on that? All right, so let's move on to the next example. This is example 11.2. And this one says clutch. A simple clutch consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed in a piece of machinery. The two plates have masses of MA equals 6.0 kilograms and MB equals 9.0 kilograms with equal radii. R0 equals 0.60 meters. They are initially separated, and plate MA is accelerated from rest to an angular velocity omega 1 equals 7.2 radians per second, and time delta t equals 2.0 seconds. Calculate A, the angular momentum of MA, and B, the torque required to have accelerated MA from rest to omega 1. C, next, plate MB initially at rest but free to rotate without friction is placed in firm contact with the freely rotating plate MA, and the two plates then rotate at a constant angular velocity, omega 2, which is considerably less than omega 1. Why does this happen, and what is omega 2? So that's our problem, and I will just do a quick drawing of this because I realize it probably would be more helpful even if students don't necessarily have uh, if they do have access to the book. Some might not later when they're looking at the video, so I'll go ahead and do it like that. So those are our two plates. This top one is MB, and MA is equal to 6.0 kilograms, and MB is 9.0 kilograms. And R0 is the same for both of them. R0 equals RA equals RB, and that is 0.60 meters. And what we found was that omega 0 was 0 radians per second, but omega 1 was equal to 7.2 radians. I don't think I could write radians any worse than I just did. Uh, anyways, radians per second is omega 1, and that takes place after a time delta t equals 2.0 seconds. As I said, for part A, they want us to calculate the angular momentum, which I'll call I initial, because that's the only thing that's rotating initially. It's MA, and it's rotating specifically in this direction like that. That would mean its angular momentum is a vector pointing straight up, for instance. Then part B, we're asked to calculate the torque required to have accelerated MA up to that amount. So I'm just going to say torque sub A equals question mark. And then part C, they want to find what is omega 2. And they want us to explain why it's different. Okay, so that's our problem. We have our normal scenario solution. Specifically, what we're talking about here is the summation of the torques is equal to 0. Now, you can imagine, for instance, whatever rotated this object, this mass MA, this disk up to the 7.2 radians per second, obviously with some torque, but it's on a frictionless axle, basically. So we have frictionless bearings for the axle, and now it's spinning. We don't need any additional torques to get that up. So in fact, what's going on now is our system is this mass MA, which is already rotating, plus the mass MB, which isn't rotating yet. And of course, when they come together, they're going to start rotating together. And that is definitely a torque on MA and a torque on MB. But those two are internal forces since we treated the system as the disk MA plus the disk MB. So with that in mind, the net torque is 0. And since the net torque on the system is 0, that means angular momentum is conserved. So we're going to say L initial is equal to L final. And that means that I1 omega 1 is equal to I2 omega 2. Before we can do any of that, though, we have to be able to calculate angular momentum, and specifically for part A, we already wrote down what angular momentum is. Then we're going to have to calculate torque, and we're going to use the summation of the torques is equal to either dl dt or I omega. Either one of those would be acceptable. And finally, we're going to use conservation of momentum, which I've already written up there. So let us start with part A. So part A, the angular momentum, actually I wrote I equals question mark, and it was supposed to be L is equal to question mark. I don't know why I wrote I there, but let me fix that. So L, the initial angular momentum, is question mark. So L sub I is equal to I A omega, what we call omega 1. So in this case, it's actually a circular disc. They specifically told us these clutches are circular discs, and we know that a disc, just like a cylinder, has the moment of inertia formula given by I disc equals I cylinder equals 1/2 mr squared. That's the formula we're using. So we're going to say 1/2 and then times ma and then times r0 squared, and that's our moment of inertia. And then our omega 1 is the angular velocity. So we can go ahead and plug all this in and say that the initial angular momentum is 1/2 times 6.0 kilograms times R0, which is 0.60 meters, and that quantity's got to be squared, times 7.2 radians per second. And when we do this calculation, we get on, sorry, I was saying on to tell my calculator to come on. I don't know why I did that. Zero point 0.5 times 6 times, making sure I used the right mass. Yes, I did. Times 6 times zero point 0.6 squared times 7.2, and that gives me a moment of inertia, or excuse me, a angular momentum of 7.78 with one extra digit, 7.78, and you'll notice the units are kilograms meter squared per second. And that is the units for angular momentum. We haven't made any kind of specific name for that unit. It's just kilogram meter squared per second. Notice I did drop the radians because, as we've mentioned before, radian is actually just a pure number, so you can always drop that radian if you so desire. So that's our initial angular momentum. I should probably write that's equal to L sub I, and I'll box that off. And that's our answer to part A. Now to part B, we want to figure out what the torque is. And the torque, of course, is basically what's responsible for delta L over delta T, or you could use I omega. I'm going to use L equals, I'm going to use torque, the net torque, is equal to delta L over delta T. And that's approximately it. It's really supposed to be the derivative, of course, but if you're taking a small enough time interval, then the delta L over delta T is pretty close. Now, what is delta L? Well, the initial, it's actually, as always, delta means final minus initial. So this would be final momentum or final angular momentum minus the initial angular momentum over delta T. Now, the final angular momentum is the momentum that it had when we first started looking at it. The initial angular momentum was zero because sometime in the past it was started from rest. So that makes this really, really easy because now we can just use the figure we just calculated, which is 7.78 with one extra digit, kilograms meter squared per second, minus L initial, which would be zero, and then all of that would be divided by 2.0 seconds because that's the time interval over which it was accelerated. So when I do that, you can get 7.78 divided by 2. Obviously, 7.78, well, anyway, 7.78 divided by 2 is 3.89. So I'm going to say 3.89, again, one extra digit beyond the significant digits. And this is going to be equal to kilogram meter squared per second squared. And if you remember what that is actually a Newton times a meter, because a Newton is a kilogram meter per second squared, and we've got an extra meter multiplied by that, so it's a Newton meter, which is the unit of torque. So that's the torque, what we called specifically torque A when I worded the problem. Any question on that? All right. Again, underlying digits are non-significant ones. It just allows us the extra digit we can carry for any subsequent calculations. Now for part C, they want us to find out what is omega 2. So we're actually imagining that all of a sudden we're going to drop the mass mb on top of it, and the friction between mb and ma is going to cause ma to slow down some and mb to speed up some, and ultimately they'll come to a equilibrium, if you will, of some speed that's lower than the speed they had before. What dictates that speed is conservation of angular momentum, because we're treating the system as if it's not just MA or just MB, it's MA and MB. And the total angular momentum, or excuse me, the total angular momentum before MB is dropped onto MA is just the angular momentum we calculated in part A. And that's going to have to be equal to the angular momentum it has afterwards, even though we're actually adding a much larger mass. We're going from a single 6 kilogram disc to a 6 kilogram mass or disc stuck to a 9 kilogram mass of the same radius. So now we can use conservation of momentum as follows. We're going to say I initial omega initial is equal to I final omega final. And what we have here is the initial moment, or the initial angular momentum, is really just that 7.78 kilograms meters squared per second. And then the other side is going to be I times omega. Well, now I is the moment of inertia of MA plus the moment of inertia of MB, and both of those are 1/2 M square R squared. So that's going to be a common 1/2, and then a MA plus MB, and then a common R0 squared because they have the same radius. And then that's going to give us, in fact, our angular final velocity, omega final, by setting all these equals. So I can say 7.78 kilograms meters squared per second is equal to 1/2 6.0 kilograms plus 9.0 kilograms times 0.60 meters quantity squared in times omega f. So omega f is going to be equal to all this junk. So I'm going to take specifically 7.78 on top kilograms meters squared per second is the numerator, and then I'm going to take 0.5 times parenthesis 6 plus 9 close parenthesis times 0.6 squared, like that, and that gives me 2.70 as the mathematical number that is the coefficient of the omega f, and that has units of kilograms meter squared. And therefore we take 7.78 and divide that by 2.7, and that gives us 2.88. Oops, switch to an eraser again. So that's 2.88, and that is radians. Remember, we can throw a radian on there anytime we want to, per second. So that, or excuse me, radian per second, singular, not squared. So that's the final angular velocity, omega f, and that's what we were asked for. And of course, they also asked us why, and the reason is conservation of angular momentum. When we treat the system as not just MA and not just MB, but MA and MB, then the total angular momentum before they run into each other is just the angular momentum that MA has. But then after they come in contact, which clearly one puts a force on the other and the other puts a force on the first, but those are internal forces, so the net external torque is still zero because of course because the axles are frictionless, and under that circumstance, angular momentum is conserved, and angular momentum conservation manifests itself through this equation, and therefore this result. Any question there? All right. Now we're going to look at example 11.3, and this one's kind of neat, especially if you're interested in astronomy. This is example 11.3. Example 11.3, neutron star. Astronomers detect stars that are rotating extremely rapidly, known as neutron stars. A neutron star is believed to form the inner core of a massive star that collapsed under its own gravitation to a star very small, of very small radius and very high density. Neutron stars, for instance, a single teaspoon might weigh as much as a Mack truck, to give you some idea. So that's a pretty big deal. Anyways, before collapse, suppose the core of such a massive star is the size of our sun. Its radius is roughly 7 times 10 to the fifth kilometers, or 7 times 10 to the eighth meters, with mass 2.0 times as great as the sun, and is rotating at a frequency of about one revolution every 100 days. If it were to undergo gravitational collapse to a neutron star of radius 10 kilometers, what would its rotation frequency be? Assume the star is a uniform sphere at all times and loses no mass. So the fact that it loses no mass means we don't have to look up the mass of the sun, which sadly that's one that I have memorized, whereas I don't keep the sun's radius memorized too well. So, anyways, let's write down what we have. We have the R initial is equal to, and since they gave us the other one in kilometers, it's okay to leave it in kilometers. So I'm just going to say 7 times 10 to the fifth kilometer. Whoa, I'm just going to write kilograms there for some reason. Kilometers. The final radius, R final, is actually about 10 kilometers. So the fact that they have the same units means that we can do the conservation of angular momentum process, and the units will just cancel out. We don't have to convert them. We do know that the initial angular velocity, omega I, is 1.0 revolution per 100 days, like that. And what we're asked to find is not really what is omega final, but specifically they ask us for the rotation frequency. They're not asking for the angular frequency, they're asking for the rotation frequency, which is the quantity F, to be honest. So we really got to make sure we do that. So solution is going to require a little bit of information. We need to know that angular momentum is conserved. Obviously, there's no net torque acting on the system. If any torque happened because of the masses interacting with the other masses in the sun, they're all part of the system, so it doesn't matter. So the summation of the torques is equal to zero, which implies uh, L initial is equal to L final, which is angular momentum. It is a sphere, so we're going to say I is equal to 2/5 mr squared. And we also have that L is equal to I times omega. We also need to know that omega is equal to 2 pi times the frequency. And to be honest with you, the revolutions isn't really a useful quantity normally, but in this case, it could be because we might want to express it in revolutions per second or per day or something like that. That's still a fairly good reference. So let us go with that. All right. Now, to do this, let's start with I1 omega 1 is equal to, or I initial, omega initial is equal to I2 omega 2 R. Did we call that final? We didn't really call it anything, but anyways, we'll deal with that. So I can put this down as 2/5, whatever the mass is, and that's not going to change. So 2/5 m times r initial squared times omega initial is equal to 2/5 r final squared times omega final. And therefore, we could actually use this to find the relationship between omega 2 and omega 1, specifically for omega 2 or omega final in this case. We can go ahead and see that the m's are going to cancel out, the 2/5 are going to cancel out as well. So, what we ultimately get for this is omega final is equal to r initial squared over r final squared times omega I, like that. Now we can also use the omega is equal to 2 pi f, so we could say 2 pi times the frequency final is equal to r initial squared over r final squared, and that's equal to 2 pi f initial. And when we do that, we can go ahead and see that the two pi's are actually going to calculate out as well. So with this in mind, we can go ahead and calculate omega final. Oops, didn't mean to switch to red. Omega final is going to be equal to 7 times 10 to the fifth kilometers squared over 10 kilometers squared, and then we're going to multiply that by the 100 revolution, or the 1 revolution per 100 days, so 1.0 revolution per 100 days. But 100 days is obviously 1 day is equal to 24 hours, and obviously 1 hour is equal to 3600 seconds. So we can do that as well. When we do this math, we get 7 times 10 to the fifth divided by 10. And then we're going to square that. That, by the way, is 70,000, obviously, but we're going to square that. And that's going to be 4.9, which is one extra digit than we really had, times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the ninth. That's just the ratio of the two radii squared. And then I've got to multiply that by the initial 1 revolution per 100 days, which that converts to 1 divided by 100, or let's say divided by parentheses 100 times 24 times 3600, and that gives me an angular, or a frequency, if you will. And this is supposed to be just plain F. I don't know why I wrote it as omega. Let me fix that real quick before I mess up. That's just going to be F sub F, and I'm sure that's why it happened. But this angular frequency that was 1 revolution per 100 days turns out to be 1.2 times 10 to the negative seventh revolutions per second. So now I can multiply that 1.2 times 10 to the negative seventh by the 4.9 times 10 to the ninth. Let me double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 9. So 4.9 times 10 to the 9. And that gives me roughly 567, which is quite a bit more figures than we really had. We really only had one sig fig, so it's roughly 567 revolutions per second. So that's pretty fast for something that was just recently a full-size star, but now all of a sudden it's about the size of Washington, D.C. In terms of diameter. Anybody have any questions on that? Okay, that is a neat history, the life cycle of stars. It turns out when stars are initially become stars, basically what happens is at some point in their core, the temperature gets high enough to fuse hydrogen into helium. That normally takes about 10 billion Kelvin. And once it reaches that temperature, then hydrogen, four of those can come together to make one helium atom. And that actually gives off, because the helium atom turns out to be lighter than the four hydrogen atoms, that gives off not only some particles, but quite a bit of amount of energy, each one of those during each one of those reactions. And that is what gives us our sun as energy. That's how we get the energy that keeps us alive. But slowly that process runs out because, at least in the stars that are about the size of our sun, the core is doesn't have a circulation mechanism. There's a central part of the star, if they're roughly the size of our sun, where the mass doesn't circulate in and out of the core. It just all stays in that core. So when you start running out of hydrogen in that core, if the mass is big enough that once it stops fusing hydrogen and helium, gravity is going to squish that core, make it smaller. If that mass is big enough, then it'll bring it up to a high enough pressure and therefore a high enough temperature to make it reach the next critical 100 million Kelvin that needs to happen for hydrogen or for helium to fuse into carbon and some other things. And it continues that process, fusing different substances throughout until eventually it runs into iron. And if it runs into iron, there's really no way out of that. You could stop, for instance, a little shy of that and not ever get to the iron state. But the main thing is, in all that process, we're just converting, sort of like making I don't know if you've ever seen people that make candles by dipping them in different colored waxes one by one, and then you open it up and it has all these beautiful colors. That's sort of what a star looks like as it's near its death, because it have like an innermost core that's fusing the most recent substance that it can fuse, and then outside of that is a little shell that's fusing the previous substance, and outside that's another one doing the previous substance before that, and then another and another and another and another. And if it actually reaches the point of a supernova explosion, then all those elements that were basically just mostly hydrogen and helium are now in abundance. We now have carbon, we now have oxygen, we have silicon, all sorts of stuff, and iron, and that's where we get all these elements from. Because as far as the Big Bang's concerned, that pretty much only produced mostly hydrogen and helium, but we have figured out that it did some trace amounts of helium, or excuse me, lithium, beryllium, and maybe a little bit of carbon. That's about it. So, anyways, that's an interesting sidebar, but let's carry on. Your book talked about the vector nature, or the directional nature of momentum, and again, it's going to be just like the right hand rule. So if something's rotating this way, then you take your right hand fingers and curl them that way. Your right thumb is pointing in the direction of it. So with that in mind, let's look at example 11.4. So example 11.4, running on a circular platform. So what we have here is sort of like a playground merry-go-round or something like that, and it's free to rotate. It has essentially frictionless axle system where it can rotate freely. But what we're going to imagine is a person walking on it, and as they start to walk, we're going to try to figure out how the actual merry-go-round is going to respond. So here's the problem. Running on a circular platform. Suppose a 60 kilogram person stands at the edge of a 6.0 meter diameter circular platform, which is mounted on frictionless bearings and has a moment of inertia 1,800 kilogram meter squared. The platform is initially at rest. Oh, excuse me. The platform is at rest initially, but when the person begins running at a speed of 4.2 meters per second with respect to the Earth around its edge, the platform begins to rotate in the opposite direction, as in figure 11.5. Calculate the angular velocity of the platform. So what we're given is little m, the mass of the person, is supposed to be 60 kilograms. We're going to assume that's two sig figs. The diameter of the platform, d, is supposed to be 6.0 meters, which implies the radius would be 3.0 meters. Uh, the moment of inertia of the disk Moment of inertia of the disk is 1800 kilograms meters squared. And I started to write that like it was going to be on top of a fraction, so apologize for that. And the person is going to be running velocity of m is relative to Earth, of course, is 4.2 meters per second. So what we're imagining is this person's running at 4.2 meters per second that way, and that's going to cause the rotation of the disk to go that way. So it's actually going to rotate the opposite way. And we're asked to find specifically calculate the angular velocity of the platform. So we're asked to find omega d. Ooh, I should write that in blue, I guess. We're asked to find omega d equals question mark. Solution. This is a simple conservation of angular momentum problem. I1 omega 1 is equal to I2 omega 2. That's what we're using here. In this case, we are treating the individual person as a person all by himself, and that's like a point particle because compared to 6 meters, a human's pretty small. At least a vertical human compared to a 6 meter horizontally is fairly small. So the moment of inertia, for instance, for that human is just mr squared. And here's the big deal. Initially, the man stands still on the platform and the platform stands still. Then all of a sudden, the man starts to run in this, what we would say, counterclockwise direction as seen from above, and the disk is going to start to rotate in the clockwise direction. So what we have is 0 is equal to I1 omega, let's say I m omega m plus I disk omega disk because initially the angular momentum is 0 and after they start then it's got to stay 0, and your book actually chose to use a negative between these, and that you can do that, but I like the actual result to show a negative to point out that hey, if we call the person's velocity this positive quantity, then we expect the disk's velocity to be in the opposite direction, and that negative tells us that, so I'm using them as both positive. So what we have here is the moment of inertia of the person, which is mr squared. That's going to be m times r squared. And then the angular velocity of the person is just v over r. So that's going to be v, I think we called it v sub m. Yeah, v sub m over r. So that's our omega and that's our I. So that's I person and omega for the person, plus now we have the 1800 kilograms meter squared for I disk, and we have omega disk like that, and all of that is equal to 0. So now we can plug in the numbers. The numbers are the following: 60 kilograms times 3.0 meters, and that's because he's running at the edge, so it's the full radius. That's going to be squared, and then we're going to take 4.2 meters per second and divide that by 3.0 meters, and that's that velocity. Let's go ahead and put the 0 on this side, and then we're going to say is equal to 1800 kilograms meter squared times omega d, and that gives us omega d is equal to negative, obviously, because once we pull those numbers, the 6 times the 3 times the 4.2, and then notice I actually said the 6 times the 3 without saying 3 squared. That's because one of these 3's is going to cancel out. So I'm going to take, and I said 6 instead of 60, 60 times 3 times 4.2 is equal to 756. Oops, there I go again with my wrong color. 756. And that's one extra digit than we had, and that is kilograms meters squared per second. That's the angular momentum before or as a result of the human running. And then we divide that by 1800 kilograms meters squared. And that gives us, divided by 1800, gives us 0.420. And notice the kilogram meter squared drop off, so that gives us radians per second is the angular velocity. And it's a negative showing that it in fact went in the opposite direction as the person is running. Any questions on that one? Again, your book chose to say that was I m omega m minus I d omega d, even though they use different symbols, but they use the minus just so they'd get a positive answer. You can leave the plus between them because it really is the summation of them that you're doing, and then the negative will just show you that one's pointed one way and the other one's pointed the other way. Any questions before we go on to example 11.5? Okay. What did I do there? I did blue. Let's do purple next. Let's do purple. Spinning bicycle wheel. So your physics teacher is holding a spinning bicycle wheel while he stands on a stationary frictionless turntable. What will happen if the teacher suddenly flips the bicycle wheel over so that it is spinning in the opposite direction? So you've probably seen a demonstration like this before, but basically if you take a bicycle wheel and instead of just having the little axles come out of the hubs there, you could actually screw on it, for instance, some handles. And that's what we do, and we use it for a physics demo. And just to make it a little bit more dramatic, we often will take, instead of a regular bicycle tire, we'll either make a tire that's made out of solid rubber, so it's quite a bit heavier, or sometimes you can even take a tire and just fill it up with like lead shot, and that'll make the edges really, really heavy, and therefore the moment of inertia will be huge because it's mr squared, and the vast majority of the m is out at the full radius r. So that's what you'd spin. And normally when we use it as an instructor, we'll take the wheel and we'll get it spinning really, really fast. And sometimes we have electric devices to get that started or whatever. But you could imagine me holding it like this and the wheel actually rotating this way so that if you look from above, it would look like it's spinning counterclockwise. If it is spinning counterclockwise, then the right hand rule suggests that counterclockwise, my fingers rotating counterclockwise would suggest the angular momentum of that wheel is in the upward direction. So if I'm holding it like this, the angular momentum of the system is up, and that's the whole thing. We're going to treat the system to be the instructor standing on the potentially spinning platform and holding the bicycle wheel. All three are parts of the system, and ideally the person wants to make sure they're sort of in the center of the disc, and you want to make sure, like, I have a problem with it because I'm a pretty good sized guy, weigh 250 plus usually, but I am more around 250 now. So I'm kind of heavy, and a little bicycle wheel doesn't make a big difference with me. But if you keep yourself closer to the center, or if you use a lighter person, it's a little easier. Of course, we wouldn't want to get students to use because it's really kind of easy to hurt yourself with that spinning heavy wheel, especially if it's spinning very fast. But we're going to be holding it like this, say, actually holding it like this, say, and what we're going to do is we're going to take and rotate it this way. So what's going to happen is initially the angular momentum is just that up angular momentum. But now if we assume that we were able to do it in such a way that the velocity of the wheel didn't decrease, but now the angular momentum of the wheel was up, is exactly the same angular momentum but down, we still have to have the initial angular momentum equal to the final angular momentum. So the final angular momentum still has to be that same little L up. So what actually happens? Well, let me explain that. So what we're going to do is we'll have this. This is the disc that the instructor is standing on, say. And let's say he's holding the wheel like this. And there's his head. And what we're saying is the wheel is rotating this way, and the angular momentum is that way. This is the initial state. And that's a fairly frictionless rotatable disc that he's standing on. So that's free to rotate. Obviously, the person has some mass and stuff like that, so that's going to be a bit of a problem. But either way, no big deal. Now we're going to draw after they flip it over. So after he flips it over, the wheel is now going to be going in this other direction, which is clockwise as seen from above. And I'll try to draw him holding the parts like that. Only now this thing has the angular momentum that it had before, only it's green because it's pointing a different direction. So that's just the angular momentum of the wheel, but it has to be equal to the total angular momentum of the system. The total angular momentum of the system still has to be equal to the original angular momentum of the wheel. So this is our final state. But in order for that to truly be the final state, then the disk that the person's standing on and the person himself is going to have to rotate in the opposite direction. So now what's going to happen is the actual disk is rotating this way. And it has to do so by the angular momentum of teacher plus disk has to be negative, or I should say positive 2L. In other words, we just have now this L is negative, and I should put that as a negative because it points the other way. And that's because, or I can say so that the summation of the angular momenta is actually equal to the original positive L because it's equal to 2L plus negative L. So you see, when you add 2L and negative L, you get just plain L again. And the negative L is what the wheel is doing now that we flipped it over, and the 2L is what the disc plus the instructor has. So luckily the instructor is a lot heavier than the wheel, and the probably the disc is a bit heavier than the wheel as well. So 2L might seem like a big deal, but it's probably not that big a deal. The person's just going to go in a clockwise direction because that was the direction or excuse me, a counterclockwise direction because that's the direction the wheel was spinning initially. Now the disc and the person maybe go very, very slowly like that as a result of them flipping the wheel over, even though the wheel's going really, really fast. Any questions on that? All right. Now, I'll tell you, this is also somewhat related to, I don't know if anybody drives a motorcycle. I used to ride a motorcycle, and I took the motorcycle training course because it gets you cheaper insurance, and it's a really good training program. It teaches you a lot of the fundamentals. It keeps you from pretty much dying, a lot of simple ways you can die by riding a motorcycle without knowing what you're doing. And just something as simple as I noticed, like when the 80s, when I used to watch Chips and stuff like that, you'd see them lay down their bike, and they would do so with stuntmen. It's not an easy thing to lay down a motorcycle at 50, 60 miles per hour without getting yourself killed. And part of the way that they were able to do that is because they understood the way motorcycles work. And one of those things is they'll teach you when you're taking the motorcycle training course is get this. Now, normally when you're riding, let's say a bicycle, you're riding your bicycle like this and you're pedaling along. And if you want to turn right, you pull the right hand side of the wheel, the handlebars to you and push the left hand side of the handlebars away from you. And then that would let you turn to the right. And that's fine. We do that all the time. However, if you do that with a motorcycle, especially when you get up to like 50, 60 miles per hour, that's not going to work at all. In fact, they teach you this, and it seems completely crazy, but I remember doing it, and I hadn't worked out the physics of it very well yet. But the instructor told us that, and I drove my motorcycle home that day, and I was like, okay, let me try this out. And I got out in a big, big open area of road where I was driving safely, had many lanes, had plenty of shoulder in case anything bad happened. But he said, if you want to turn right, you have to push right. So get this, I'm still wanting to turn right now, but in order to turn right, you push the right handlebar forward. Now that just seems crazy. I mean, it's literally turning the handlebars the opposite way as you remember from a bicycle. But the reason is this: is conservation of angular momentum. It turns out that when you're riding a motorcycle forward, say, then the angular momentum of the tires is to your left. The front wheel is rotating this way, so right hand rule says it's going this way, and then the back wheel is going that way as well. If I go to apply a torque, let's say this direction, which is the right hand side going forward, then that's a torque this way. That torque pointing that way has to be compensated for by the bike switching. It's sort of like the example we're going to do in a second, where you take a bicycle wheel and it's spinning really hard and you try to lift up and it ends up going right. That's exactly what happens with the motorcycle. The motorcycle, because you try to put a torque on it this way, the tires have so much angular momentum, they're going to try to maintain the angular momentum of the system, and they correct accordingly. And that actually causes the bike more or less to lean over to the right. And when you lean over to the right, the radius of the tire is a little bit smaller, so you actually make a turn. That's a way of describing it. But that is a something they teach you in a motorcycle training driving course. And if you watch Chips, you'll notice that when they go to turn, they sure enough push that side forward when they go to turn right. It's crazy. I always just pictured it because I'd ridden regular bikes, freestyle bikes, half pipes, quarter pipes, pools, flatland, that kind of stuff, and sometimes very fast. But at high speeds, you don't really think very much about turning the handlebars. You pretty much just lean and it goes that way. And that's the way I was treating the motorcycle. And that works, but it's sort of counterintuitive and I should say it's just kind of weird to do it that way. Once you learn to do it the other way, you'll find that you're a little bit more in control of the bike and stuff like that. So hopefully that's interesting to you guys, or hopefully y'all learned something from that. Let's move along. The next section was cross product, and I've done that ad nauseum. I even calculated one last meeting with just some regular vector components. They do an example 11.6 with some regular force and radius vectors, or lever arm vectors. So you can check that out, but you can also check out my video or any of my other videos on my YouTube channel. So we're going to go on past that and move on to section 11.3, and specifically move on to conceptual example 11.7. So conceptual example 11.7 is a little more easy to follow than this last one. I might not write it down. I'm just going to read it. So conceptual example 11.7, a particle's angular momentum. What is the angular momentum of a particle of mass m moving with speed v in a circle of radius r in a counterclockwise direction? So what they tell you here is the value of angular momentum depends on the choice of the point O, meaning O is the center of rotation for your system. Let us calculate L with respect to the center of the circle. Now, L is supposed to be R cross P. All right, we learned, or excuse me, we learned that in the first day of chapter 11, the radius vector that points from O to the point at which the particle is moving is the vector r, and then the particle has a linear momentum m times v, which is p. So r cross p is our angular momentum. If the object is actually going in a circle, though, then the velocity and the radius vector, the lever arm, or the r from zero to the particle, are perpendicular to each other, and we know that the magnitude of a cross product is m times r times v times the sine of the angle between MV and R. But in this case, the angle is 90 degrees, so it's M times V times R times the sine of 90, which is just MVR. So that gives us the angular momentum. Well, the angular momentum, if you remember, also happens to be equal to I times omega. And if you replace the V with R times omega, or specifically, if you recognize that V is R times omega, then you can substitute the V in MVR and you'll end up getting MR squared omega. MR squared omega is exactly mr squared, the moment of inertia for a point particle at a distance r away, times omega. So let me just show you that equation wise, since I know sometimes students don't really follow arguments like that mathematically in their head. So this is going to be example 11.7, and I knew as soon as I started explaining it that I was I was screwing up. But basically L is equal to R cross P, and P is equal to MV. If you're actually talking about something going in a circle, though, like that, then That is your r vector. And then your individual particle might be here. And your velocity vector v is like this. And specifically, I think they said going clockwise, didn't they? Because I just drew that counterclockwise like a jerk. Oh, they did say counterclockwise, so that's cool. All right, so when we calculate r cross p, we can calculate the magnitude because the magnitude of L is equal to the magnitude of R cross P. And of course, we know that the magnitude of a cross product is the product of the magnitudes of the vectors. So R times P, and then times the sine of the angle between them. Now I'm going to make use of the fact that P is equal to MV, and that's going to give me R times M times V times the sine of theta. Well, we can see right here that clearly theta is equal to 90 degrees, and I should have drew that a little bigger. Theta equals 90 degrees, and of course, sine of 90 degrees is equal to 1. So this gives us m times r times v. Or we might even write it as, just to be provocative here, uh, m times r. And now I'm going to replace, since v equals r omega, I'm going to replace the v with r omega, and that's going to give me m r squared omega. But remembering that L is equal to I times omega, you see, oh, I for a point particle, which I already told you was mr squared, is in fact mr squared. And the moment of inertia, of course, or the angular momentum, of course, is I omega. Any questions on that? All right, so that's what I was talking about. Now we'll go on to section 11.4, and that's where they talk about derivations. They do the derivations of Newton's second law for rotation. They do it for an inertial reference frame. Then they consider if they actually take it through the center of mass, then they can do it for even a non-inertial reference frame. So that gives us the equations that we need. And I've already given you those equations, so we can move on. But still, as much as you can, I highly recommend you read this so you can follow what they're talking about. It might take you a little while. It might take you on the order of an hour to read this one section if you're actually trying to make sense of it. But read it. Try to actually have the pictures out and available. Try to have a piece of paper with you so you can do calculations as you go along, and hopefully it'll make you better understand it, and you'll be in a much better place, for instance, than I was when I finished the equivalent section in my textbook. It took me probably a couple more weeks after that was over before I started to understand it, and I still would say I didn't understand it until probably I took the next course, which is a whole year of just like the equivalent of 241, but much more advanced. But it wasn't until I took that course that I even got that. So anyways, let's move on to the next section, which is 11.5, angular momentum and torque for a rigid object. So we're talking about rigid bodies, and rigid bodies are just objects who are so solid. I've been using the Rubik's Cube as one of those cases where basically the distance from the center of this square to the center of this square is not going to change. If I rotate this really, really fast, then I might get so fast that the plastic that makes up this Rubik's cube, might actually fail, and the springs holding it together might actually fail, and then it would no longer become a rigid body, and the distance between the center of this square and the center of this square wouldn't be the same anymore. But not only that, if you take the angle that between the two vectors, let's consider a vector that points from the center of the center square to the center of this bottom square, and then take the vector that points from the center of this center square to the center of this diagonal square right here. Those two vectors have an angle roughly 90 plus 45 or 135 degrees. A rigid body also has that angle is never going to change. That's what a rigid body is. It's not only that the distance between particles, any two particles, is not going to change. It's also that the angles connecting two particles to one another, and then the angle between that line connecting and a line connecting one of those particles to another particle, that angle is not going to change as well. Okay, so let's jump into example 11.8 called an Atwood machine. I think I did one right. So example 11.8. Now, this is a slightly different way of doing Atwood's machine. We could do it with F equals ma and the summation of torques equals I times alpha, but your book is doing it a neat way, so I want to show you that way. It says Atwood machine. An Atwood machine consists of two masses, ma and mb, which are connected by an inelastic cord of negligible mass that passes over a pulley. If the pulley has radius r0 and moment of inertia I about its axle, determine the acceleration of masses ma and mb and compare it to the situation where the moment of inertia of the pulley is ignored. Ignore friction at the axle. Now, we're also going to go on in general when you go to solve this type of problem. If you want to figure out velocities and stuff like that, you could also have to relate the velocities of MA and MB to each other by the string not stretching. That links them such that if MA goes down by 1 inch, then MB is going to go up by 1 inch. And if MA goes down by 1 inch in 1 second, then MB is going to go up 1 inch in 1 second. So that means the velocity of MA is equal in magnitude to the velocity of MB. If you also consider that the mass MA goes down 1 inch in 1 second and then 2 inches in the next second, then MB is going to go up 1 inch in 1 second and then 2 inches in the next second. And that shows us that the acceleration magnitude of MA is the same as the magnitude of the acceleration of MB. That's some of the stuff we would normally use as well. But let's start off with the figures. So we're told that we have a MA and we're told that we have a MB, and we're told that we have a radius of the pulley that's R0, and we're told that the pulley has a moment of inertia I, and that's about it. Let me go ahead and draw a diagram so we'll have some idea what we're talking about here. And I'm going to try to use my software's ability to make my drawings better. It's so hard to draw a circle on a frictionless tablet like this. But what we're looking at here is roughly the center of the circle. And what we're saying is this distance is R0. And now hanging from it are two masses. I'm going to try to draw a nice line here. That did okay. And we'll try to draw a nice line here as well. That did fairly okay. Now I really want it to be coming off the pulley, and the same thing for this one. I really want it to be coming off the pulley instead of some weird stuff right there. Okay, so now I'm going to draw a box. Oh, that's great. I'm going to draw another box. These are supposed to be nice square boxes. They're not turning out so well, but that's okay. This is MA, and this one is MB. And we have, of course, a mass, or actually a moment of inertia I there. We have everything else we need. Now, normally I would draw free body diagrams and all that stuff, but we're actually wanting to do this the way your book does. And specifically, we're going to use angular momentum. It says, we first determine the angular momentum of the system, then apply Newton's second laws. So solution, torque, the summation of the torques, is equal to dl dt, like that. Okay, that's for one dimensional. And if we're talking about something just rotating this way, then the torque vector is actually just a one-dimensional sort of thing, so we don't have to worry about the vectorness of it. But now we're going to go ahead and calculate the angular momentum. So we're going to imagine, for instance, that this whole system is moving up with some specific speed v there, and that of course means that this one's moving down with a speed v, and since the rope is probably not slipping along the edge of the pulley, then we could also say that this pulley has an angular velocity omega given by v over r that points that way as well. So that's something we can work with. Now I'm going to use all that and calculate my moment of inertia, or excuse me, my angular momentum, and we're going to assume that clockwise rotation, which is not what I usually do, but in this case I'm going to assume that clockwise rotation is a positive rotation. So that's a positive angular momentum, so on and so forth. Now, what is that angular momentum? Well, that angular momentum, remember, is r cross p. So we're going to use L is equal to r cross p for the individual masses because they're, kind of small. But what that means is you could say that the magnitude of the angular momentum is the component of r perpendicular to the p, r the component of p perpendicular to the r, just like we learned for torque earlier. So with that in mind, the velocity is actually perpendicular to the radius vector. So the angular momentum is just going to be the mass times the velocity times the radius. So that's going to give us ma times v, that's our angular, that's our momentum, and then times r0. And then we're also going to get another one for mb. That's going to be mb times v times r0. Notice all of that's completely consistent with rotation in the clockwise direction. And then we have the moment of inertia of the actual pulley because that's part of the system too. So that angular momentum L equals I times omega. That's going to give us I times omega, but omega is, since V equals R omega, omega is V over R, so I'm going to say this is I equals V over R0 like that. So we could make that a little simpler by maybe factoring out a MA, or we could factor out a V or whatever, but your book does it this way. I'll go ahead and use it. MA plus MB times VR0 plus I times V over R0 like that. So that's our angular momentum. Now we're going to calculate our torque. And of course, the torque, I'm going to consider a torque in the clockwise direction as positive as well. So that means the torque caused by the MB is a positive torque, and the torque caused by the MA is a negative torque. So that's going to give me MB times G, that's the actual force. And then the force, of course, is exactly perpendicular to the lever arm, and the lever arm has a length of R0. So that's going to be MBG times R0. And then the other one's going to be a minus, and that's going to be MAG times R0 like that. That's the total torque. Now what we can do is we can say the summation of the torques, and this really is the summation of the torques. It's not just the torque, but the summation of the torques is equal to dl dt. So we can go about doing that as follows. I'm going to go ahead and factor out the common terms in the summation of the torques, and that's going to give me mb minus ma times, now I have a common G times R0, and that's the torque side. So I'm going to say this is that. And then we're going to say that is equal to dl dt. So in this case, I'm going to say d by dt of, and now I'm going to use my ma plus mb times V times R0 plus I times V over R0 like that. And we're going to take, of course, the derivative of all that. When we take the derivative of all that, we're going to get the MA and the MB not changing, but nor will the R0 change. So we're going to get MA plus MB times dV dt times R0, and that dV dt is a derivative acting only on the V because the R0 is a constant. And then the I and the R0 is a constant, so that's going to be I over R0, and I'm going to get a dV dt over here. So that is what we call the total Newton's second law. Now we can also make use of the fact that A is equal to dV dt, and when we do that, we can solve for A. So what we have is MB minus MA times GR0 is equal to MA plus MB times R0 plus I over, that was supposed to be an R0, I over R0, and then all of that times dv dt. In other words, I just factored out the common term of dv dt, which is our acceleration. Let me go ahead and write that accordingly. Oops, that was supposed to be an eraser. So dv dt, and what I'm saying is this quantity is going to be a, so I can solve for a. And when I solve for a, I'm going to get a is equal to, as I said, dv dt, but that is actually equal to mb minus ma over ma plus mb. And notice there's a factor of R0 up here. I'm going to put that in there as well. And this would be MA, MB, R0 plus I over, in this case, yeah, I'll just leave it like this. Oops, lost it. I over R0. And we're almost there. Now what I'm going to do is multiply by 1 over R0 on both sides, or on the top and bottom. So I'm going to say times 1 over R0 over 1 over R0, like that. And now when I get that, that's going to give me the following. MB minus MA over MA plus MB plus I over R0 squared. And then all of that technically, ooh, and I left that off before. I was actually holding a factor of G that I never wrote next to it, but I'll write it there for starters. Okay, and now I just put it out here because this makes it look more like the formula that we got when we worked the Atwood machine with a massless pulley. And in fact, our answer is A is equal to MB minus MA over MA plus MB plus I over R0 squared, all of that times G. And that is our acceleration. And if you consider as I goes to 0, meaning the like the pulley's massless or something like that, then you end up getting A is equal to MB minus MA over MA plus MB, all of that times G, which is exactly the formula that we got for the Atwood machine when we did it with a massless pulley. Anybody have any questions on that? All right, so let me go through this example, conceptual example 11.9. So conceptual. So what we're looking at here is I'm going to imagine a bicycle wheel like the one we were talking about earlier. And oops, like that. So that's going to represent our bicycle wheel. And we're going to say this is our little hub right here, and this is our little hub right here as well. And we've got hanging from this a little axle, and then hanging from that on the other side is another little axle. And what we're going to imagine doing is we're going to take our hand. Actually, let me draw. I think I can do a little better than that. We're going to take our hand. Oops. And imagine trying to rotate it specifically this way. Okay. Now, the wheel is actually spinning this way before we do that. And because it's spinning that way, the right-hand rule tells us that our angular momentum vector L is this way. And what it's asking is, suppose you are holding a bicycle wheel by a handle connected to its axle, as in figure 1117A. The wheel is spinning so that the angular momentum L points horizontally along the y-axis as shown. Now you suddenly try to tilt the axle upward along the z-axis so that the center of mass moves vertically. You expect the wheel to go up, and it would if it weren't rotating, but it unexpectedly swerves to the right. Explain. Take the system as the wheel, axle, and the handle. Your hand is external. Okay, so now I can also assign this to a coordinate system. We're going to imagine, for instance, that this is our y-axis, and then coming out of the page is our x-axis, and then vertical, but in the page, is our z-axis. So when I go to turn it up by doing my hand like this, okay, that means the torque that's actually in the direction. Notice if my hand is doing this, that means the torque is actually that way because, well, actually it's this way, okay? So rotating it this way as if it is rotating about, oops, that's really bad, about the x-axis. Okay, so what I'm meaning is when I rotate my hand, it's just like I'm rotating it like that around the x-axis. Rotating my hand as if it is rotating about the x-axis means, oops, means the torque I am applying is in the positive x direction by the right hand rule. So rotating this way, notice my thumb is pointing at me when I'm doing that, but that's what my wrist is trying to do. My wrist is like this, holding the wheel like this, and I'm trying to lift that way. So that's the equivalent of my hand rotating that way. And you can see that my thumb is actually pointing towards me. So the torque direction is in the positive uh, X direction. Now, here's the big thing. The summation of the torques is equal to dl dt is the equation we're using. And in this case, we're really only imagining there being one torque. So this is going to be about equal to torque is equal to delta L over delta T. And this is inherently a vector equation. So with that in mind, the change in angular momentum, delta L, should be the torque times delta T. But T points in the positive X direction. So delta L also points in the positive X direction. So if our initial angular momentum is L, and let's draw this coordinate system so we'll know what we're talking about. There's my Z, there's my X, there's my Y, and then all of a sudden my torque is this way. Then my delta L, which equals torque times delta T, is that way as well. Therefore, what we get, again, drawing the axes, there's y, there's z, there's x. We're going to have L initially is this way, but now I've added to it a delta L, which is parallel to the x-axis, and that gives us a resulting angular momentum, L plus delta L. I tilted my iPad, so now it looks like multiplication instead of addition. L plus delta L is this way. And that's literally meaning, hey, I tried to lift the wheel up and it went to the right, which is exactly what we're asked to explain. It says, suppose you're holding a bicycle wheel by a handle connected to its axle, as in figure 1117a. The wheel is spinning so that its angular momentum L points horizontally to the right along the y-axis as shown. Now you suddenly try to tilt the axle upward along the z-axis so that the CM, center of mass, moves vertically. You expect the wheel to go up, and it would if it weren't rotating, but it unexpectedly swerves to the right. Explain. So as we saw, the new angular momentum, when I try to apply a torque in the positive x direction, the new angular momentum is going to move to the positive x direction because that's the direction of the torque. So just like when I turn my steering or my handlebars of a motorcycle by pushing the right forward, that is in fact a torque upward, and the angular momentum is going to change to the upward direction. The angular momentum was this way, so now it's going to add to this on my motorcycle. So now my angular momentum's this way, which means the motorcycle is going to tilt over. And tilting over is the way we normally turn before we learn that crazy rule that pushing right makes you turn right. Any questions on that? I highly, highly, highly recommend you reading through the chapter or the section above and below figure 1118. So try to read about figure 1118. So I want you to read that a lot. I want you to read it and try to think it out because it's good thinking and it explains a lot and it's really useful, and it goes into understanding, for instance, how people balance their car tires. So, for instance, when you first buy a car, it actually comes with new tires and all that good stuff, unless you buy a new used car. And sometimes then it comes when it's not balanced. But one of the things is if your tire's not balanced, your car will go like that and all sorts of crazy stuff like that. So we often try to balance it. And it always seemed weird to me because they actually would put these little weights on the rims and that would actually balance it, which obvious, I mean, it makes sense because you could say, okay, well, maybe my tire's really heavy at what's right now is the bottom. So if I want to counteract that, I could put a weight right there at the top to compensate for it. And that would make sense. But the way they test it is they get that wheel spinning really, really fast. And then the machine says, blah, 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 and they cut the machine off and then it turns it to something on the machine, and then they put the weight right there where the machine's indicating, and they do that and you don't really understand why or how that works. Well, if you start by understanding a figure 1118 and then you go through rotational imbalance and talk about figure 1119, then you'll start to make sense of that. So I highly, highly, highly recommend you really putting in the time and resources to read the paragraph or two before 1118 and then the paragraph or two before 1119, and that would help you a lot. Uh, I'm going to skip that 1110. That's something for you to read, and I'm certainly not going to ask you about that because it took me a while to figure that out myself. So I just think that's a little bit much to test on, but it's certainly the sort of one of the holy grails of trying to learn as much about this material as you can. So certainly have it as a goal, even though it's not necessarily something I'm going to test you on. All right, let's go to example 1111, and this one's kind of neat. It says example 1111, Kepler's second law derived. Kepler's second law states that the area each planet moves so that a line from the sun to the planet sweeps out, excuse me, Kepler's second law states that each planet moves so that a line from the sun to the planet sweeps out equal areas in equal time. Section 6.5. Use conservation of angular momentum to show this. So what we're going to do is we're going to imagine a orbit for a planet, and the orbit for the planet is something like that. And of course, we know from Kepler's first law that the planets travel in elliptical orbits with the sun at one focal point. I'm going to put the sun, let's say, right here. Oop, I'm going to make it square, evidently. There you go. It made it circular this time. And what we're going to do is imagine a coordinate system in which sort of the sun is the center of the coordinate system. And I'm going to take a vector that points from the center of the sun to the location of a particular planet at a particular point in the orbit, let's say right there. Now, that vector is going to be the position vector if you treat the origin of the coordinate as the center of the sun. We know in reality the sun's actually doing a little bit of a wobble on the order of a meter across as a result of all the other planets orbiting around it in and out of phase and stuff like that. But generally speaking, it's pretty small compared to the 7 times 10 to the fifth meters that are 7 times 10 to the fifth kilometers that the sun is. Now, if you allow this velocity of this particular planet, so let's say the planet is a nice purple planet like that. If you imagine it actually traveling with some velocity v, and let's say that velocity is, of course, obviously tangential to the ellipse at that point, that is our velocity like that. And in fact, since that's the velocity, if you multiply the velocity by a small amount of time, dt, you'll get a small amount of distance. Okay, so what I can do then is imagine, oops, I went to do that in black. You can imagine another position vector. Ooh, that's too small. I need y'all to see what's going on here. So I'm going to say like that, that, that. So that's the actual area that's going to be swept out after a time v delta t, and it's supposed to be really, really small. It's a little bigger than I really meant it to be, but that's okay. This distance is v delta t, and in fact, if you take and extend this r vector out like this, you would say that this angle right here is, let's say, the angle theta. And then you could imagine, for instance, that this v vector can be broken up into a component that is parallel to the r, and then another component that is perpendicular to the r, like that. And this component is given by v times sine theta, and this one would be v cosine theta, like that. Okay. So in that differential amount of time, we could say that the differential area appears to be a triangle. So dA is equal to the formula for a triangle, 1/2 the base, and the base of this triangle is the vector r, and the actual height of the triangle, if you will, is the component of v perpendicular to r. So that's v delta t, or v dt, if you will. Actually, let me call that dt instead of delta t. So we're going to say that the other part of the actual vector, the component of the velocity that's perpendicular to the r, which is going to make a right triangle, is of course v dt, and then you've got to multiply that times the sine of theta, like that. So that would be the actual area swept out in a small amount of time dt. And I've shown it way bigger than it should be. That angle between r and the dotted r is quite a bit larger than I wanted to show. But the main thing is you can see that that v component would make a little bit of a right triangle, at least on a small section. And then you'd have just a regular triangle, and the area of the triangle is 1/2 base times height. And we're saying the height is the v that's perpendicular to the r, and that is obviously v sine theta. And the distance that's traveled during a time dt is v sine theta times dt. So that's our differential area element. If I wanted to calculate the actual derivative of area with respect to time, that's dA over dt, I'd get 1/2 RV dt sine theta over dt, and that gives me 1/2 RV sine theta. And I forgot to write what example this is. This is example 11.1, 11.11. Okay, so that's our derivative of the area with respect to time. And it doesn't seem like you're getting anywhere, but remember, we're supposed to show that it sweeps out equal areas in equal time. And what we can realize now is that since L is equal to M times R times V times the sine of theta, because that is the formula for angular momentum. Remember, angular momentum, L, is equal to R cross P, and that means the magnitude of L is equal to the magnitude of R times the magnitude of MV times the sine of the angle between them. So these two equations come together to make that, and we can see, oh, that dA dt looks a little bit like MRV sine theta. In fact, it only differs by a 2m, and from that, we can put these together. We can say this with this gives me the following. Specifically, dA over dt is actually equal to L over 2m. Or I can write it as 1 over 2m times L. Because notice, if I now take the L right here and I divide that by 2m, that would get rid of the m and it would put a 1/2. So it'd get rid of here and put a 2, and that would be 1/2 RV sine theta, which is exactly what we had here. Now, the main thing we're supposed to know is it puts out equal areas and equal times. That is true if this quantity, L over 2m, is a constant, and we know the net external torque on the system is 0. Or let me write it with green. Since the torque equals 0, or I should say, since torque equals 0, we know L is a constant. And M is a constant because it's a planet. We're not expecting the planet to be losing any weight. Therefore, dA over dt equals a constant. And that means, for instance, that the area swept out during a given amount of time might be dA, and that dA is equal to some constant times dt. And that is exactly what we set out to prove, specifically that the area in a given amount of time is always going to be the same. So dA over dt, or specifically dA, is equal to some constant that's never going to change times dt, and we're done. So we can write QED. Anybody have any questions on that one? All right, there's another neat example. We've got about 30, yeah, we've got about 33 minutes, so plenty of time here. I'm going to go to example 11.12 now. This one's pretty straightforward, but it's neat, so I like it. It says bullet strikes cylinder edge. A bullet of mass m moving with velocity v strikes and becomes embedded at the edge of a cylinder of mass big M and radius r0 as shown in figure 1122. The cylinder, initially at rest, begins to rotate about its symmetry axis, which remains fixed in position. Assuming no frictional torque, what is the angular velocity of the cylinder after the collision? Is the kinetic energy conserved? So that's the big question we're trying to answer. What we know is we have a bullet of mass little m and velocity v, and we have it hitting a cylinder of mass big M and radius r0. And assuming no frictional torque, we're going to say friction is negligible. Oops, negligible. One of my first physics instructors spoke Portuguese as his first language, and he said negligible. He just pronounced it in the sort of the wrong syllable, or yeah, he enunciated the wrong syllable. That always comes to mind when I hear negligible. Dr. Giustiniano was a good guy. So F is negligible, and the cylinder's initially at rest. So omega zero is equal to zero. Rotation about its symmetry axis. We got that. Assume no frictional torque. What is the angular velocity of the cylinder? So we want to know omega final equals question mark. And we want to know, is kinetic energy conserved? Is K conserved? So those are our big questions. Let me go ahead and draw a figure of this so we can have some idea what we're talking about here. Okay, there I am using the features of this device pretty well. So what we have here is the center of the cylinder is right about here, and we're going to say that this is our lever arm vector in some sense because you can imagine this bullet's going to hit the edge, and that's going to cause a torque on the actual cylinder, and therefore we need to have a lever arm, and the lever arm is just a vector that points from the center of rotation to the point at which the torque or the force is applied. In this case, it's where the bullet hits. So over here, we're going to imagine that a bullet is coming, and this bullet has a mass m and a velocity v, and then it's going to embed in that. And because of that, I'm going to say copy. Now I'm going to say paste. Now, because of that, the bullet is going to embed into the actual cylinder like this, but now the cylinder is going to be moving like this with an angular velocity omega. And what we're asked to do is calculate this new angular velocity. So what we're going to treat as the system is we're going to say the bullet and the cylinder are the system. So the bullet, it doesn't necessarily seem like it, but it does have an angular momentum because remember, angular momentum is r cross p. And if you consider, for instance, initially what the lever arm or what the r would be for the bullet, it would be this vector right here, like that. And remember, L is equal to r cross p, and p is equal to mv, and the magnitude of L is equal to, one way of saying it is R perpendicular to P, R P perpendicular to R. In this case, we see the velocity and therefore the momentum, P equals mv, should be that direction. And if I take the component of R that's perpendicular to the P, in other words, I use this version, then I just get R0 times P, which equals R0 times M times V. So we can now say conservation of angular momentum So conservation of angular momentum gives us that L initial is equal to L final. And we know that's true because the only forces that are acting, if we assume it's frictionless and all that good stuff, the only forces that are acting is the force of the mass of the bullet hitting the cylinder and the cylinder applying a force to that bullet. Well, those are internal forces because our system includes the bullet and the cylinder. So, with that in mind, we can go ahead and say that R0 times m times v is the initial angular momentum, but after the fact, we're going to have two, well, actually, this is a cylinder, so it's going to be one half m r0 squared times omega final. That's the angular momentum that the cylinder has all by itself. But in addition to that is the bullet embedded in it, and that bullet is a particle, and that's going to have a angular momentum given by m, because the mass is pretty much going to be. I mean, it could be split all out, but basically it's all going to be a distance r away. So it's going to have a mass m at a distance r0 away. So the angular momentum or the moment of inertia for that would be mr squared, and then its velocity will be whatever the new velocity it has is, but that happens to be translated or related to the omega f by v equals r times omega f. So omega, or so I can say v is actually just equal to r0. Uh, our omega should be, I could just write the omega. That's what I'll do. Omega f like that. Okay. So that's what we got here. We can see that we don't have a common mass that can drop out. So we're going to have to go ahead and work this out brute force. So I've got R0 times M times V is equal to 1/2 M R0 squared plus M R0 squared. All of that is times omega F. So omega F turns out to be M times V times R0 divided by 1/2 M R0 squared. That I wrote that really small. Somebody just came in. Let me get them. So 1/2 big M R0 squared plus little m r0 squared like that. That should be the final angular momentum, or that should be the final angular velocity of it. Now we can go about calculating. If I wanted to, for instance, I can go ahead and make this a little smaller by realizing there's a common factor of r0 everywhere, in which case I can then say omega f is equal to mv over 1/2 m r0 plus m r0 like that. And I could actually leave the m plus m, the m plus 1/2 m inside and put the r0 on the bottom outside of the parentheses. All of that's fair game. But now we want to figure out basically what is the change in kinetic energy, specifically delta K is equal to K final minus K initial. Well, K initial is 1/2 mv squared. K final, on the other hand, is 1/2 I, and what we found for I is specifically 1/2 mr0 squared plus mr0 squared times then it's 1/2 I omega squared, so it's omega final squared like that. So if I wanted to find out what delta K is, I'd say delta K is equal to K final minus K initial, and that is obviously given by a constant factor of 1/2 that's going to be out in front. So I'll just put that 1/2 out in front, and then I have 1/2 mr0 squared plus mr0 squared times omega f squared minus, and here I'm going to put a bracket here, minus m v squared like that. And we can go ahead and substitute in this new version of the angular velocity to make it, of course, it's going to get a lot of algebra in it, but we can deal with that. It's 1/2 times Now I'm going to have 1 half mr0 squared plus mr0 squared times omega f is going to be m squared v squared. It's omega f squared, by the way. So it's m squared v squared over 1 half mr0 plus mr0, and that quantity is going to be squared as well. All this is times that, and then minus m v squared like that. So that's actually the result, but we can work the algebra out a little bit more. And if you play with it a little bit, your book says that it's going to come out to be, and I'm just going to trust them on this one because we're running a little shorter on time than I'd like. I think I am, anyways. So this is going to turn out to be little m times big M over 2 big M plus 4m, and all of that times v squared. Because you can see we now have a v squared that's common to everything. Really, what would probably help is use the original version of the of the omega f instead of using what I did, which was this version. If I use this version, I'd have the 1 half mr0 squared mr0 squared down here, and that would help me get rid of that over there. So that's the way I should have done it, and that would have given me a little bit more ease in jumping into this. But anyways, I think that's enough for right now as far as that algebra goes. Let me check and see if there's any more examples that I really wanted to get. I think that was the last one I really wanted to do. Yeah, we then start subsection 11.7, which is a spinning top and a gyroscope. And that talks about precession, which is something that's super valuable. For instance, one of the major arguments that I say major, one of the really bad arguments people have made against anthropogenic global warming is that we're not taking into account the fact that the Earth precesses. Well, the Earth does precess. Basically, what's going on is the Earth has a little bit bulbous center. In other words, its equator is a little larger radius than at its poles, and it's tilted like this. So at all times, the gravity of the sun is trying to pull it upright like that. But as it does that, the Earth actually moves a little bit that way, and then it pulls this way, and then it pulls that way, then it pulls. That actually makes the axis do this. Well, it turns out that if you calculate that precession frequency, or if you just look at the ancients, we've actually got enough data. We can tell exactly what the period of it is, and it's only the order of I want to say 40,000 years, but I haven't taught astronomy in probably almost 10 years, so I don't remember the numbers off the top of my head, but roughly that sort of thing. So it turns out, yeah, we do take into account the precession of the Earth's orbital or a rotation axis, and that does make a difference. But we would only see that in such a long time period that it doesn't matter. What we're seeing over the last, well, since 1650s, roughly 1650, no, 1750, somewhere around there. Since that time, it hasn't been a large fraction of the precession period for the Earth anyway, so that doesn't matter. But anyways, it's a really neat, interesting thing to read, but I'm not going to test you on it. And specifically, the result is basically that the omega, which is the precession frequency, is equal to m times g times r over L, where L is the angular momentum and r is the actual distance between the center of mass. And in the case of a top, it's actually the distance between the center of mass and the point that's touching the ground or the floor or the tabletop. So again, we're not going to do anything with that, nor are we going to do anything with rotating reference frames and non and inertial forces and these so-called fictitious inertial forces. The one thing I will tell you that about is I don't know why this just came up the way it did. Just lost my There it is. Okay. So the one thing I did want to tell you about the Coriolis force, again, not making you do any calculations with this. I just want to let you know the general rule is, and you learn this in any geology class or whatever, but basically in the northern hemisphere, the Coriolis force compels things to turn to the right, and in the southern hemisphere, it compels them to turn to the left. So if you think about, for instance, planet Earth, and we'll draw planet Earth right here, that's supposed to be a circle roughly. That's our equator. if you had a low pressure zone right there, again, I'm not showing any land masses. All I care about is the actual atmosphere and that sort of stuff. If it's a low pressure, then we know there's what we call a pressure gradient force, and that literally means dP over dx or dP over dr. It's a gradient that you'll learn in Calc 3, but it's specifically the derivative of the pressure with respect to a lateral position parallel to the Earth's surface. And that radiant or that pressure gradient causes the wind to actually converge on low pressure zones like this. So this is what low pressure zone would normally do. If it wasn't for the Coriolis force, this would be what would happen when we get a low pressure zone. But because of the Coriolis force, all of these masses of wind are going to be deflected to the right. So instead of them just turning to straight towards the center, they're going to do this, turn to the right. Gonna do this, turn to the right. Gonna do this, turn to the right. To the right, to the right, to the right, to the right, and to the right. So that ultimately what you get is a rotation like that, and that's supposed to be what you expect. Now, in addition to that, there's friction forces, and that's going to cause it to do a little bit differently. But the main thing is in the northern hemisphere, we're basically going to have low pressure zones with counterclockwise rotations. And that's all because of the Coriolis force. And as I mentioned before, that is not the cause of toilet spiraling the direction they spiral. If you did actually take one particular toilet and you flush it here in the northern hemisphere, and then you take that same toilet and run it down to the southern hemisphere, even at the same latitude but negative or the reverse of the latitude, and go down to the southern hemisphere and connect that toilet and flush it, it's going to flush the same direction. Spiral, the water is going to spiral down the drain in the same direction at both locations. But that is ultimately what causes the hurricanes to actually spiral around as opposed to just converging in like that. And that's basically it. I should mention that the Coriolis force is really sort of a it's not really a force as much as it's actually more of a acceleration that should be on the right hand side of F equals ma. But if you put it on the left hand side, it has the opposite effect because it's an opposite sign and it looks like a force instead of part of the acceleration. But in reality, it's just part of the acceleration that comes from taking, for instance, the unit vector r is equal to r hat of theta and phi. So if you talk about, for instance, cylindrical coordinates, then r hat, I should say r hat, would actually be cosine theta I hat plus sine theta j hat. You see that it specifically has there's a theta in there. It specifically has a theta dependence on it. Not in this case, it doesn't have a phi dependence, but if we actually did that with with spherical coordinates, so this one's cylindrical. If you did that with spherical coordinates, it's a little more complicated, but let me show you roughly what that is because it does come in handy knowing these coordinate systems. So if this is x, this is y, this is z, you could take this point in space right here, draw a straight line down, then this corresponds to the y coordinate, this corresponds to the x coordinate, and this corresponds to the z coordinate. So that point is called x comma y comma z. But you can do better than that too. You could use the spherical coordinate system and you'd say that this is the coordinate r. You could say that this is the coordinate phi and this is the coordinate theta, so that you would actually have this as r theta phi. Okay, so and by the way, this down here is sometimes called rho, and rho would be equal to r times the sine of phi. And that rho is actually the cylindrical r that we talk about up above, but this is the spherical coordinates. So if you take the time to compute what the little r hat vector would be, as well as the little phi hat vector would be, as well as the basically the xy plane theta hat vector would be, you could work those out. But the r hat really is the main thing, and you would say r is equal to r times r theta phi for this case because it is going to work out to be r theta phi. Specifically, you can see that r hat is going to be cosine theta times sine phi. It's cosine theta sine phi I hat plus sine theta sine phi j hat plus plus cosine phi k hat. That's really what r hat is in spherical coordinates. Now then if you took dr over dt, which is d by dt of r times r hat, then you could say it's going to be dr over dt times r hat plus r times dr hat over dt. But dr hat over dt is equal to dr hat over d theta times d theta over dt plus dr hat over d phi times d phi over dt. And if you apply that chain rule repeatedly against the sines and cosines and all that, and then you remember, of course, that theta hat, or excuse me, theta dot is actually equal to omega, and theta double dot, which is a second order derivative, is actually equal to alpha, and stuff like that. Once you apply all that, you will actually get the Coriolis force coming out as part of that acceleration on the right. But that's more than what you needed to know, and I just thought I'd share it with you a little bit. It's always nice to know that about spherical coordinates. The cylindrical coordinates, just to give you a quick rundown on what that would be, the cylindrical coordinates would be, again, x, y, z, but this time all we measure is the rho, the theta, and the z up, so that that point becomes x, y, z, but it also becomes rho theta z. And with that, of course, becomes a rho hat, which is just in the xy plane, and therefore looks like this quantity. And then perpendicular to that, 90 degrees ahead, but also in the xy plane, is theta hat, and then vertical is k hat. So that's the parts of the cylindrical coordinates. All right, you all are free to go. I'll wait here till the last person leaves in case anybody has any questions. Don't forget you have a test due this, or actually not you guys, you had your test during lab today. I did have a couple people that had excuses so that they can take it a little later, but they have to take it online. And if they didn't have excuses, they have to lose points. So I apologize that some people got a little bit of an advantage, but they had excuses, so we let that go. So that also means don't talk about it because you might be giving someone an unfair advantage. But make sure you get the online test done. Hopefully you saw my emails today. One of my students, Ashton, who had just left a second ago, he let me know that he was having problems with the online test, and I think I fixed it. If y'all have any questions about that, y'all can ask me now, or you can send me an email or a text message later. But you're free to go. Thanks. Have a good weekend. Have a nice, safe weekend, and let me know if you need anything. Thanks, Jacob. Thanks, Cameron. All right. Well, that looks like it. So stop sharing. Thanks for coming, everyone. Bye bye.